Hi, I'm AMBENZON. Today, I'll present a paper titled Validation of Artificial Neural Networks to Model Acoustic Behavior of Induction Motors, originally published in Applied Acoustics. The authors aim to leverage artificial neural networks, or ANNs, for accurate acoustic modeling. This presentation will follow this structure: introduction, problem statement, methodology with a focus on their ANN model approach as relevant to our course, results, discussion, and conclusion. Induction motors are widely used but generate noise that impacts comfort and efficiency. This noise comes from mechanical, aerodynamic, and electromagnetic sources. Traditional models struggle with nonlinear noise prediction, especially when environmental interference is present. The paper explores the use of ANNs, particularly multitask learning models, to predict multiple noise parameters simultaneously. The paper aims to predict psychoacoustic parameters, namely equivalent sound pressure level, or LAEQ, loudness L, roughness R, and sharpness SA. Nonlinear noise prediction is complex due to environmental interference. ANNs are proposed as they can handle nonlinearity effectively and support multitask learning, making them ideal for this problem. The experiments were conducted using three-phase induction motors with the Lander type squirrel cage, capable of adjusting the number of poles to vary motor speed. Testing was performed inside a semi-anechoic chamber compliant with ISO 3745 standards to eliminate external noise interference and ensure accurate sound measurement. Sound measurements were captured using GRES46AE preamplified microphone set calibrated with a B&K acoustic calibrator. Electrical parameters were recorded using Fluke 435 Series 2 power analyzer, sampling at 256 samples per cycle. Motor power was controlled by Semicron Semitech inverter, which used pulse width modulation, or PWM, techniques to generate signals with frequencies up to 20 kilohertz. Control signal Control signals for the inverter were generated using LabVIEW software, while sound and electrical data were captured using Samurai software on a Panasonic CF18 Toughbook. Microphones were mounted on tripods and positioned to capture noise directly from the motor. Each microphone was individually calibrated before testing to ensure precision. Noise data was collected under various operating conditions such as motor speed, number of poles, and PWM modulation parameters. Each test recorded data for 10 seconds once the motor's harmonic stabilized, ensuring consistent input conditions. The model used 40 input features, including harmonic distortions in voltage and current, modulation indices from the PWM techniques, motor parameters such as speed and the number of poles, voltage and current harmonics across a range of frequencies. As mentioned, the study used ANNs to model the acoustic behavior of induction motor. Let's take a closer look at how the ANN in this study is structured and trained. The model starts with an input layer that has 14 neurons. Each neuron represents a specific feature from the experimental data, like harmonic distortions, motor speed, or number of poles. The hidden layer uses two types of neurons, namely sigmoid units, or SUNN. These are great for approximating continuous functions, but they have downside. They often get stuck in local minima, which can limit their performance. Second is the product units, neural networks. These are more efficient for capturing complex relationships because they handle multiplicative interactions. Plus, they require fewer neurons, which helps keep the model simpler. At the end, the output layer has four neurons. Each one is tasked with predicting a specific psychoacoustic parameter, namely sound pressure level, loudness, roughness, and sharpness. To make the ANN work effectively, the researcher used evolutionary algorithms for optimization. These algorithms work like a natural selection process. They tweak the model's weights and structure iteratively, favoring the changes that improve performance. This approach avoids some common problems of traditional backpropagation, like getting stuck in suboptimal solutions. The dataset was split with 75% used for training and the remaining 25% for testing. Both PUNN and SUNN models were trained over 200 generations. The training process carefully balanced the number of hidden neurons to prevent overfitting. Throughout the process, the goal was to minimize mean squared error, or MSE, and ensure the model could generalize well to new data. Once trained, the models were evaluated using several key metrics. One is the mean squared error, or again, it's simply MSE. This metric measured how accurate the model's predictions were. The second one is the standard error of prediction, or simply SEP. This assesses how consistent and reliable those predictions were across the test data. The researchers also considered the number of connections and input features to ensure the model remained efficient without overcomplicating things. This study highlights that the PUNN or yeah, PUNN performed better than the SUNN. Specifically, PUNN achieved a mean squared error of 38.77 and a standard error of prediction of 13.11, which are strong indicators of its accuracy and reliability. What's impressive is that this performance was achieved using only 10 input variables, showcasing the model's efficiency in multitask prediction without unnecessary complexity. It's a clear example of how well designed neural networks can effectively balance simplicity and performance. The paper emphasizes the strengths of these models. One key point is their ability to maintain high accuracy while reducing complexity, which is often a challenge in neural network design. The multitask learning approach is particularly valuable because it allows the model to predict multiple outputs simultaneously, saving time and resources compared to training separate models for each parameter. The application for this research are also exciting. These models can be integrated into predictive maintenance systems, enabling real-time noise monitoring to prevent issues before they arise. Additionally, there's a potential to deploy these models in smart industrial environments, helping reduce noise pollution and improving overall operational efficiency. To wrap up, the study demonstrates that multitask ANNs, especially PUNN, are highly effective for modeling the acoustic behavior of induction motors. The research shows that increasing the fundamental harmonic of the power signal improves sound quality, particularly at lower motor speeds. However, overall, this work illustrates how ANNs can handle complex nonlinear system while delivering practical insights for industrial noise reduction and acoustic quality control. Having explored how ANNs can model acoustic behavior in industrial settings, let us now turn our attention to another fascinating application of machine learning in agriculture. The next study, titled Detecting Tomatoes in Greenhouse Scenes by Combining the AdaBoost Classifier and Color Analysis, investigates how the AdaBoost Classifier and Color Analysis can be combined to efficiently detect ripe tomatoes in greenhouse environments. This research exemplifies the innovative use of computer vision to address challenges in precision agriculture. Let's dive into the challenges of tomato detection in greenhouses. Unlike controlled lab environments, greenhouses pose unique issues like varying light conditions, occlusions from leaves and twigs, and the fact that tomatoes can have a similar color to their background. This study proposes a practical solution by combining the AdaBoost classification algorithm with a color analysis technique, all using standard RGB images. The goal is to create a reliable, efficient system for detecting ripe tomatoes in real world agricultural settings. The data set used in this research consists of 180 images taken under natural daylight using and Nikon J2 digital camera. Each image captures the complexity of greenhouse conditions, including overlapping tomatoes, varying illuminations, and occlusions. From these 156 samples of ripe tomatoes and 877 background samples were cropped and labeled for training. To ensure computational efficiency, the images were resized to 388 by 260 pixels. All processing was done in MATLAB on a standard 2.8 GHz Intel Pentium processor, showcasing the feasibility of this approach without the need of high-end hardware. The algorithm works through five clear steps. First, it scans the image using a sliding sub-window approach. Then it extracts hair-like features, patterns like edges, lines, and curves within each sub-window. Next, an AdaBoost classifier determines if a region contains a tomato. To refine this, a color analysis using the eye component from the YIQ color space is applied, which helps eliminate false positives. Finally, overlapping detections are merged to ensure accurate localization of the tomatoes. It's a smart, multi step process that balances precision with computational simplicity. The AdaBoost classifier plays a central role here. It combines multiple weak classifiers into a single strong one through iterative learning. In this study, over 20,000 iterations were used to fine tune the classifier and reduce errors. Hair-like features originally developed for tasks like face detection were adapted to identify tomato characteristics such as the edges and curves. By focusing on these features, the algorithm remains robust against varying illumination, which is often a challenge in greenhouse environments. The results are compelling. The proposed algorithm detected 96.5% of ripe tomatoes in the test set, outperforming other methods like BB neural networks, which achieve 86%, and support vector machines at 91.2%. False negatives were ripe tomatoes were missed, stood at 10.8%, while false positives were only 3.5%. These numbers highlight not just the accuracy but also the efficiency of this approach, making it a viable option for agricultural robotics. What makes this study stand out is its practicality. The algorithm uses standard RGB images, avoiding the need for expensive sensors, which is a game changer for cost sensitive industries like agriculture. It handles challenges like uneven lightings and partial occlusions effectively. However, there are limitations. It struggles with tomatoes that are heavily occluded or grown in diverse cultivars, which highlights the need for further optimization. But overall, it's a significant step forward in precision agriculture. In conclusion, this study presents a highly effective method for detecting ripe tomatoes in greenhouse environments by combining HAR-like features, the AdaBoost algorithm, and APV-based color analysis. The approach not only achieves high accuracy, but it's also practical and scalable, making it a strong candidate for guiding robotic harvesters in real-world conditions. While currently tested on a single tomato cultivar, the results demonstrate the feasibility of using RGB images for precision agriculture. Looking ahead, this method could be further enhanced to handle occluded tomatoes, accommodate diverse cultivars, and operate in more complex environments.